G'day mates, this is Hamaki Engli, your Quantum Odyssey tour guide. Today we are on the 8th day, so the second week, and today we will talk about controlled gates. So last time we've talked about that gates work in parallel. For example, if you apply an X gate on a multi-qubit system, then you have to apply the X gate on all pairs of wires which differ by the one qubit that the X gate is being applied to. The same goes for the Z gate and all single qubit gates. We've also explored implicitly that we can also put gates in parallel. For example, an X gate on the 0th qubit and an X gate on the 1st qubit is equivalent to putting an X gate on both qubits in parallel. So that's like the gate depth. Today, we will discuss about your first truly 2-qubit system, the controlled gate. The controlled gate allows you to apply an X, or in fact like any single qubit gate, provided that all of the control bits are set to 1. So this allows you to selectively perform like swaps on any pair of qubits on lanes which differ only by 1 qubit. But even then, like directly, there are some limitations because the control bit has to be 1 for this to work. However, you can compose controlled gates to apply a controlled X when the control gate is 0, and you can also perform swaps. By using the techniques with controlled gates, you can actually perform any permutation of the sigils, provided that you have studied some group theory, permutations, or even like basic statistics. So the symbol for the control gate in the game is this white symbol there, which is, I like to affectionately call it the C gate. Technically, it's not really an individual gate. This diagram over there represents C1, C1X, so that means apply an X gate on the 0th qubit if the first qubit is 1. So the lanes which the first qubit is 0 are unaffected. Only those which the first qubit is 1 are affected. Then we have the CZ gate, so C1, Z1, which 0, which you will also learn is the same as C0, Z1, called controlled Z gate. Finally, this is an example of a generalized Toffoli gate called a controlled. So C2, C1, then any quantum gate, let's call this U, which is this symbol over there. There you might learn some bit of linear algebra. Basically, over there, you will later learn that all quantum gates are mathematically represented as matrices. For example, this could mean alpha, alpha, beta. So the first from the first from the second, then let's say gamma, so the second from the first, and then delta. Okay, so let's give the first introduction to the control gate. So the first controlled gate you will learn is the controlled X gate. or C naught. So C naught gate, the sigil diagram looks like this. So on a 2-qubit system, the left half would be straight, so it does nothing, and the right half would be crossed, so X. So the diagram would be this in the qubit circuit view. So it's the puzzle view, so C, then X. CX. So you can imagine a sigil. A sigil on the 0, 0 qubit would remain in its place. Same goes for 0, 1, would stay in its place. But if it is like 1, 0, it becomes 1, 1. Likewise, we have 1, 1, it becomes 1, 0. So basically, you want to say this. So falls down there. The red one falls down there. The green one falls over there. And then the yellow one falls back to the 1, 0. So here is a mnemonic for the CX gate. So we have this. So let's say CX 0, 0 becomes 0, 0. C naught X of 0, 1 becomes 0, 1. C naught X of 1, 0 becomes 1, 1. C naught X of 1, 1 becomes 1, 0. Likewise, we can say this is like a branch. So C naught X of 0, then let's 0A is equal to 0A. Likewise, C naught X of 1A is equal to 1, then not A. So likewise, we have this stuff. Sorry that my writing is a little bit off, but let's move the writing a bit closer. Okay, let's try applying a C on the other qubit, and then an X there. So we have this. We have XC. XC. Then what happens? Okay, so in this case, the lanes which are zeros at the right qubit remain unchanged. But those which are on the left on the ones on the right qubit, that means the right member of each adjacent pair switches spots. Okay, so now let's color the sigils colors. So blue still remains blue. So now we have this qubit now. Blue, red, yellow, green. Now the green falls from 1, 1 to 0, 1. So now it's from 1, 0 to 0, 1. The yellow remains in the same place, and the red moves all the way to the right. In this case, the diagram will go like this. The leftmost remains the leftmost. the second leftmost becomes the rightmost. The ones on the right side move left. So there's this thing seems to have like a left shift of the last three lanes. Finally, let's apply another CX over there. Okay, now let's draw how the sigils flow. So it's still going to be blue. Now the green still remains in place. However, the reds would move left one spot, the yellow would move right one spot. So now notice that on the top and on the bottom, it seems like the two middle lanes has been swapped. So the diagram would look like this. So we've built a C0 and swap. The swap gate is notorious for being a two-qubit system that is prone to errors on many quantum computing machines, and it is especially so for like these IBM superconducting machines. And also the IBM qubit connectivity, like it's not like a fully connected graph, so you may have to like use swap gates, a sequence of swap gates actually, to move from one qubit to the next. So this is a demonstration of the C0s and the swaps. Let's try another example. So let's try inverse C0, C0, C0 gate. So let's consider this circuit. So we have X, then we have C, then unitary gate, then X. So how would the sigil view be like? So X would imply a pair of crisscrosses on two adjacent wires. Then we have a CU. CU, okay, so that's slightly wrong. Let's put the thing on the X on the opposite sides. X before and after the C, and then the U on the other qubit. So now, how would this circuit look like? So X on the first qubit would mean crisscross over there. Then we have, let's do the other one. So this is the diagram for the X on the first qubit. Then we perform a CU gate. So the U gate would only be applied on the right half. And then the transformed qubits on the right half will be put back to the left. So putting an X between like the C's has the effect of inverting the polarity. So inverts, so prepares a controlled gate when control qubit is at 0. So this has the effect of applying a controlled operation on the left half. So let's demonstrate that. So let's say we have a qubit on the left half. So now the left half would temporarily be transported to the right half over there. Then it would be applied any transformation. So let's say transforms into that. And then after, it would be put back to its original position. So the x is there only to so that the left hand side will be applied the controlled unitary gate. So this is the diagram for that. Well, on the other side, anything on the right hand side, let's mark it as red, would be put to the left and would skip the circuit that has been applied the U gate and then back to its original position. Over there. So this 3-gate sequence is equivalent to this. So x, cu x of, let's see, beta alpha is equal to this. It's going to be beta alpha if beta is equal to 1, and then beta not alpha if beta is equal to 0. Finally, we will explore the Toffoli gate. So the Toffoli gate is the classic 3-qubit gate. Toffoli means controlled, controlled not. So, and it is just as easy to implement as any other controlled gates. Toffoli gate is nothing more than CCX. So this is a Toffoli gate on the second and first qubit, controlling the 0th qubit, and on the sigil view, it will look like this. The Toffoli gate can be used to implement any classical computation. So can implement any classical gate, which will be discussed in a future episode. So Toffoli gate. And then finally we have like a Fredkin. second gate would be this C swap. C swap is visualized as this. So the left hand is intact and the right hand will be the swap. Likewise, the Toffoli gate, you can visualize this as this. The left hand is this. So the left hand is I and the right hand would be CX. Likewise, the left side of each would be the I and the right hand of each. Let's draw this way. Would also be visualized as a CX. So you don't have to, like, the order of the C's does not matter in this case. Lastly, we will focus on a small puzzle that does something with the C gate exercise. So on one of the puzzles, we have this I, X. Then we have Y. Then we have S and I. So this is the gate that you have. So how would you draw this? So these 6 gates are fixed in this puzzle. So it will go like this. An X on the first qubit would look like that. So crisscross in pairs. Crisscross in pairs. Now we have a Y on the second qubit. So now we have crisscross from the left to the right. So it's a little bit hard to draw, but and finally an S gate on the right. That means the left. That means the right half gets the S treatment. So what happens in this case? You want this qubit to pass through, so that's what you want. You want this qubit on the left to be unaffected. So, and you're only allowed to use control gates. Right now, we have the blue sigil pass through from the first to the third links, or like in binary terms 0 to the second link. Then it would change color from blue to green using the Y gate as it moves to the right half, and then the green turns into a red as it passes through the S on the second qubit. Okay. We want to like apply a C gate, a C control on the Y. What happens? Okay, so if we add a control on the first qubit, that means the part which the middle qubits is 1, so it's just these two pairs would be applied the Y gate, and the other two would be unaffected. So now the graph would evolve into this. Now we apply another C gate. This time, anything which is on the left half of each adjacent pair, if it has not already been spared, would be spared. Finally, we apply a C gate on S. What happens? Okay, so in this case, this means the first qubit would have to also be 1 for this to happen. So in this case, the first qubit is 0 on these two lengths. So then it would also be blue. So this, technically you only need like 1 C on the Y to solve this puzzle, but I hope you are able to get this idea done. Like and subscribe to this channel. I really appreciate gaining a lot of subscribers, and as we approach Good Friday, please note that this video will be remade and be explained further. And technically, like only the first 5 minutes of this will explain you the basics of the gates. Again, like and subscribe to my channel. I will remake all of the first ring puzzles, and I hope this video will get like sponsorship as well, so I can focus on more content that has to do with both quantum computing and Lie algebras and high performance computing. Thank you.